In this video, we're going to look at the derivative of the exponential function. So we'll take some positive value a, and we'll look at the derivative of the function a to the x. And just a quick reminder, a little sketch of what an exponential function looks like. It continuously grows to the right. Since anything to the 0 is 1, a to the 0 will be 1. So if I plug in x equals 0, I get f of x equals 1, and I just have this incorrect here. This should be, of course, 0, 1, my mistake. So if we plug in 0, a to the 0 is 1, and the function is always positive. And we can see here that the limit as x approaches infinity of a to the x, well, you get some number multiplied by itself infinity number of times, and this, of course, is infinity. And the limit as x approaches negative infinity of a to the x, well, we can rewrite that as the limit as x approaches, we'll move the infinity to the x, so this is going to be the same thing as x approaches infinity of a to the negative x, which is the same thing as the limit as x approaches infinity of, well, we have a negative in the exponent, so that's the same thing as 1 over a to the x. And here we get 1 over larger positive values, so this goes to 0. So you can see, as x gets bigger and bigger, f of x, or a to the x in this case, gets bigger and bigger and bigger. And as x gets more negative towards negative infinity, we can see that a to the x goes to 0. It has a horizontal asymptote to the left at x equals 0. So that's our function there. Let's write down the derivative. So we know the definition. That's going to be the limit as x approaches, sorry, not x, we'll do it the h definition, as h approaches 0 of f of x plus h, so this is going to be a to the x plus h minus f of x, which is a to the x all over h. Now let's do a little simplification here. So a to the x plus h is the same thing as a to the x times a to the h using our exponent rules. So we'll write that down. The limit as h approaches infinity, or sorry, h approaches 0, of a to the x times a to the h minus a to the x over h. And you can see that we have a common factor of a to the x in both terms in our numerator. And that has nothing to do with our limit. Our limit involves the variable h. So a to the x is acting like a constant inside this expression since h is not varying. So we can take that a to the x and we'll factor it out, and in fact we'll factor it all the way out in front of the limit. So we get that this is the same thing as a to the x times the limit as h approaches 0 of a to the h minus 1 over h. So there we go. And the next question is, well, what is this limit that we need to calculate? This ends up being fairly difficult to compute exactly, so what we'll do is we'll talk about it numerically. And just to give this a name, I'm going to call this limit here, since whatever value we pick for a will change the value of this limit, I'm going to make this kind of a function that depends on a. I'm going to call it c of a. So we have this function c of a, and let's explore what happens when we take various values of a. And this is just from our textbook, so this is in our CLP textbook, and this is section 2.7. So, what happens if we let a equal 1? Well, that's just the function f of x is 1 to the x. And that's not very interesting, because we know any power of 1 just gives you 1. So that bit there isn't particularly interesting. We get 0. And now let's see what happens if we fix a to be 2. And what we're going to do is we're just going to estimate our limit. We'll plug in smaller and smaller values of h. We'll let h approach 0. And if we do so, you can see that this limit approaches, it looks like 0.6931 to 4 decimal places. And we can see what happens if we fix a to be 3. And here we see that the limit, plugging in h equals smaller and smaller values that approach 0, that it looks like we get something approaching 1.0986. And just for fun, what if we let a equal 10? Well, we get something like 2.3026 as our limiting value. But the whole point is that wouldn't it be nice if there was some value in here, definitely between 2 and 3, so that this limit actually equaled 1. It looks like it'll be pretty close to 3. So if we were in that case, if we found where c of a equals 1, then the derivative of that value a, of a to the x, would just be a to the x times c of a, but in this case that's just 1, so we just get a of x. So the derivative of a to the x is the same thing, a to the x. So let's go to the next slide and look at that. So what we'll do now is we will try and hone in on that value of a that gives us this limit equaling 1. And so we knew that c of 2 gave us something just less than 1, and c of 3 gave us something greater than 1. And if we look at this function, we know that exponentials are continuous, we know that, of course, constants are continuous, and we know that polynomials are continuous. In this case, it's just a linear polynomial, h. So if we do arithmetic with them, we're still going to get a continuous polynomial in their domain. There's going to be no weirdness. So if we know that c of 2 is less than 1 and c of 3 is greater than 1, there must be some place where between 2 and 3 where you get exactly 1. So we'll try and hone in on this. So if we plug in 2.5, we get the value 0.9162. So here we have something less than 1, which means now we know somewhere between 2.5 and 3, we transition to between less than 1 and greater than 1. So let's go halfway again. Let's go to 2.75. If we plug that into our function c of a, we get 1.012. That's greater than 1. So the first time we found that we needed to look, say, in this bit. And if we take half of that interval again, it tells us that we have to now be in this bit. We need to transition from something just below 1 to something just above 1 without any jumps, since we know our function is continuous. So there must be a place where is exactly 1. So we can keep this idea up. If we plug in halfway again, 0.625, which is right here, we get something less than 1, so we know we need to be in this bit of our interval between where it goes from less than 1 to greater than 1. And we can keep continuing this process. Again, we go halfway again to 2.6875, and we get something less than 1. So we know we have to look in this bit of our interval, and we continue that process over and over again, and we can hone in on this value, 2.71828, and it goes on repeatedly. It's an irrational number. It has an infinite non-repeating decimal expansion, and it comes up all of the time in mathematics, in fact, so often that we usually give this number the name E. So this number, roughly 2.71828, we call E. And what's nice is by our argument before, we get the following fact about this number, E. Remember, we're looking for the derivative of things to the x, and e to the x has this very nice property. Remember before, we said that it's going to be whatever number to the x times that function c of e. But remember, we developed this number e, so that c of e was just 1. So we indeed know that this is just going to be e to the x times 1, which is e to the x. So we have that the derivative of e to the x is just itself. So that is amazing and a very important and useful fact. So that gives us one exponential function. What about other exponential functions? Well, it turns out that for everything else it's almost the same. And in fact, we're going to introduce some notation before this. I don't keep writing log base e of x. That's fine. But a lot of times, because this e is such an important and a natural number in some sense, in the way that that number to the x, when you take the derivative, you get the exact same thing. That's why it's kind of natural. We call this the natural log of x. So we have the special notation for this particular logarithm. So in general, the derivative with respect to x of a to the x, remember, a is some positive number. Well, it's going to be kind of the same thing. It's going to be a to the x times something, that c value, c of a. And we'll show a little bit later, once we learn something called the chain rule, that that's just going to be the natural log of a. So we'll see this very shortly, why this is true. But we can indeed take the derivative of any exponential function now. That is fantastic. So let's do a quick example here. So let's say we have the function x times e to the x, and we want to find its derivative. Well, we can just use the product rule here. So the derivative of our function is going to be the derivative of the first thing, which is 1 times the second function, plus the first function times the derivative of the second function, which in this case is e to the x. And we can simplify that to get x plus 1 times e to the x. And maybe just for fun, let's look what happens when we take the derivative of that. So let's take the derivative of the derivative of x. And I'll use two little primes there to say that I'm taking the derivative twice. It's called the second derivative. So the derivative of the derivative. Well, I can do this in two ways. Maybe I'll do it using the product rule just like before. So I'll take the derivative of the first function, x plus 1. The derivative of x is 1. The derivative of 1 is 0, so we just get 1. Now we'll take just the second function, e to the x. And then the other way around, this first function, x plus 1, times the derivative of the second function. But remember, e to the x is that special function where the derivative of e to the x is itself e to the x. And we can simplify this. Here's x plus 1 e to the x's. Here's an additional e to the x, and we get x plus 2 e to the x's. And you can kind of see a pattern here. If we took the derivative instead of just twice, if we continuously took the derivative, let's say n times, and I'll use this notation to say n of these primes, so I'm taking the derivative of the derivative of the derivative n times. So, using the same idea, this is going to be x plus n times e to the x. So every time you take the derivative of this function, you get, each additional time you take the derivative, you get an extra copy of e to the x. So that's pretty interesting.